So in this video, we're going to look at both conceptually and mathematically the energy transformation and the conservation of energy. And not that they're the same thing, but they definitely work together. As we showed in the previous experiment, you can have multiple transformations of energy, and that's mainly because there are different forms of potential energy. So we have sort of an umbrella term here where potential energy is ultimately unused or stored energy, but that can come in many different forms. So one of the ways you can think about this is just as you can store data in a whole bunch of different drives, well, you can store energy in a whole bunch of different ways as well. Unused forms of energy could include, but they're not limited to, of course. You can have what we call gravitational potential. So if I write gravitational, and that's one that we've already done previously. So that's your PE is equal to mass times the force of gravity times the height of the object. Then we have chemical energy. And that's often what you see in chemical reactions. And so I'm just going to write chemical reactions over here. So as bonds are built, they have stored energy within those chemical bonds. And then we have, and I'll put it to the side here, elastic energy, where you have an object that is stretched or compressed, and as a result, all the energy from the particles that it's composed of get either compressed or spread out over a certain area. And so it has a bunch of stored energy until, of course, you release that object. So elastic energy, and that has the formula, we can write E for elastic energy of half kx squared. But this formula over here is going to be in later physics courses. And any of those forms of energy can be converted into kinetic energy. And we can think about kinetic energy largely as movement. And that can be movement of an entire object or particles. Okay, so even at the microscopic level, you can have kinetic energy. And when we think about particles moving up and down or vibrating, that's often synonymous with heat. So heat or thermal energy are just more specific forms of kinetic energy. Okay, now what I'm going to do is I'm going to draw the arrow going this way, because at the same time, you can transform kinetic energy to potential energy. So this is really a fully exchangeable process. Let's look at a simple scenario and see how energy does transform from just simple movements of objects. So let's say we have an object, in this case a person, going up a hill. Now at the bottom of the hill, so I'm going to label this the bottom. At the bottom of the hill, they begin to run or move. Well, when they move, they're exhibiting kinetic energy, or KE. And that would be full kinetic energy at the bottom of the hill. Now, as they move up the hill, and I'm going to draw an arrow going up the hill here. As they move up the hill, they start to slow down, right? And that slowdown, remember, nothing is without a cause. That slowdown is they're losing kinetic energy and they're gaining potential energy. What you can think about is that they're losing kinetic energy at the cost of increasing potential energy. So as they slow down, your EK decreases and your EP, and we're going to put, I'm writing EK, but I should write PE or KE. Your potential energy increases. And then let's say we get to the top of the hill here, so I'll mark that with a green little stick figure. What happens when we get to the top of the hill? Well, that's where we rest, right? So I'm going to write at rest, which means that our EK is 0, but our EP, right, or I'll rewrite it like I did before. We'll say your PE, potential energy, is full or at max value. So what we want you to understand is that potential energy and kinetic energy are inversely proportional. So as you increase in potential energy, your kinetic energy decreases. And that's a vice versa process. So as I increase in kinetic energy, I'm going to decrease in potential energy. Now I want us to think about what happens if we're going to go from the top of the hill to the bottom of the hill. And I'm going to use a different color. We'll use a purple arrow to exhibit that. So let's say you begin at rest, and then we move downwards here. So we're going to write at rest where the potential energy is full, and then we move downwards. Well, right before we clock the bottom of the hill, as my potential energy decreases, my kinetic energy increases. And so what you'll notice is when you start to go down a hill, your legs involuntarily start moving faster and faster to the point where it becomes really, really hard to stop. And that's because you're naturally increasing in kinetic energy. You're really accelerating, which increases your final velocity, which means in turn it's increasing your kinetic energy. So as my potential energy decreases, because my height gets smaller, my speed increases, and my kinetic energy at the same time also increases. And we're going to say over here that at that bottom of the hill, where PE is equal to 0, your kinetic energy is going to be at its max value. And so what we want you to understand is while they're interchangeable, the value of the energy never changes at all. There is no energy gained or lost. So that dealt with the transformations of energy in the various ways that energy can go from a certain type of potential energy to kinetic energy and vice versa. Now, regardless of how many transformations there are going to be, your total mechanical energy must never change. So what we say is that energy cannot be created or destroyed. And what that means is that the total amount of mechanical energy from start to finish must remain the same. So we would say that in physics, in this way, that the total energy input must equal the total energy output. And each one of these can either be potential or kinetic energy. So I can have an input of potential energy, and then that leads to kinetic energy, or I could start off with a certain amount of kinetic energy, and that'll result in potential energy. But the input has to equal the output. So what that means is if my object has stored, let's say, 50 joules of potential energy, as it starts to move, it is eventually going to dish out 50 joules, no less or no more, of kinetic energy. And so because of this, and this is a principle of thermodynamics, because of this we could say that your PE initial, and we don't even have to say the initial, let's just say the potential energy, because it's not always going to be the initial. The potential energy is equal to the kinetic energy. And all that's really saying is that the amount of energy you start off with must be the amount of energy you end off with. And this, of course, expands into mass times gravity times height, which is equal to half the mass multiplied by the speed squared. So our first example reads, a 3.0 kilogram boulder is dropped from a height. If its speed right before it strikes the ground is 7.0 meters per second, what height was it dropped at? So we know that energy can't be lost, and that in this case, and I'm drawing it out, it's dropped from some sort of height here, and right at the bottom, it's 7.0 meters per second. Okay, so what is the height here? Well, we know that it basically goes from potential energy to kinetic energy. So when we write our equation, potential energy is equal to kinetic energy, and then we write the formulas. mgh is equal to half mv squared. All we really got to do is sub in the information that's been given to us. So in a different color here, in orange, I'm going to write the mass, 3.0 kilogram multiplied by 9.81 meters per second squared, multiplied by the height, which is what's unknown, so I'm going to highlight that, is equal to half multiplied by 3.0 kilograms for the mass, multiplied by 7.0 meters per second squared. So I rewrote this over here, and that gives me 73.5. So I just computed this side of the equation to simplify my calculations. Now what I'm going to do is I'm going to divide each side by 3.0 multiplied by 9.81 in order to get it to the other side. And then what you're going to do, follow the BEDMAS rules. We're going to compute this first, then divide it. That gives us 73.5 divided by 29.43. And then that would be 2.497 meters. Now, because the question originally gave us two significant digits, we're going to round the second digit over here. And that would actually amount to 2.5 meters. All right, in our final example here, and this is an example that often people get stuck on. If you do the algebra properly, it should be okay. So an object is dropped from a height of 2 meters. What is its speed before it hits the ground? Okay, so you have the object being dropped. That tells me right away that it's going to be my potential energy is going to convert to kinetic energy as it falls down and goes faster and faster. Now the problem is, where's the mass? Because in the previous question, we've given you mass, and in any question we ever solved for kinetic energy or potential energy, there's always been a mass given. So at first glance, it'll appear like we have two unknowns then. Well, again, do the algebra properly. So I'm going to write my potential energy is equal to kinetic energy, which expands into the mass times gravity times height, which is equal to half mass multiplied by the v squared, or speed squared. And if we do the algebra first, so let's say I'm going to isolate for my speed. First, I think it's easier to change the half into 0.5, so you're not going to be working with a fraction. So I'm going to rewrite this as mgh is equal to 0.5 m and then v squared, and keeping in mind that what we want is that v squared. So now what I'm going to do, standard algebra, I want to move the 0.5 and the m to the other side. So we'll divide both sides by 0.5 m. And so now my formula reads this: mgh over 0.5 m equals v squared. Well, look at that. Your m's in math, what happens when you have, let's say, x over x? Well, the x's cancel out and you're left with 1. So if you think about these like an x, your m's are going to cancel out anyway. So there really is no need to even give you the mass in these problems when energy is conserved. So now, what we just have, and I'll draw an arrow here to rewrite it, we have gh over 0.5, and that's going to equal v squared. And then to get v and not v squared, I'm going to square root both sides. So now I just have v is equal to the root gh over 0.5. I plug in my values in the calculator as follows. And keeping with the significant figures, I end up getting a value of 6.3 meters per second.